Thank you. So our next speaker today is Yassine Eben Aimine from OneSpin, which is a Siemens business. He's a field applications engineer there, and he's going to be speaking on leveraging ML and AI in OneSpin's formal tools, use cases and opportunities. Yassine has more than 20 years experience in the EDA industry. Throughout his professional career, Yassine has partnered with design and verification engineers to deploy the latest technologies and EDA tooling in the areas of design for test, functional verification, and functional safety. Over to you, Yassine.
Thank you. Thanks, Sarah. Thanks, Mike, and thanks for continuing to organize the DVClub Europe. Certainly a very interesting event. Thank you for giving me the opportunity to talk about how OneSpin leverages ML and AI through use cases and opportunities. As you've seen from the previous slide, we're using the Siemens template. Obviously, OneSpin is now part of the Siemens and part of the Siemens EDA division. So please allow me to read out the general disclaimer. So the material that I'm going to present is subject to changes and errors. The information given in this document only contains general descriptions. Any performance features may not always specifically reflect those described and so on. And all the product designations may be trademarks of Siemens AG. So with that out of the way, let me walk you through the agenda. So I've organized my talk so that I give a general introduction to AI and ML and how it pertains to EDA. I'm actually approaching this today from two angles. One is how does OneSpin help their customers verify ML accelerators and ML designs that are implemented as hardware. And here I'm going to touch on two topics: SystemC for verification and floating point unit verification. And then I'm going to also go through how ML itself, so machine learning algorithms, are used in OneSpin to improve their formal verification tool capacity and throughput. And then I'm going to finish with a conclusion. So to start with, an introduction. Please allow me to start with a very light and scientific definition of artificial intelligence. Is it a threat? Is it an opportunity? What's artificial intelligence? Typically, we tend to think about artificial intelligence as the ability of non-organic life to perform tasks that are often attributed to human intelligence. And this is typically silicon chips buried inside robots, computers, and so on. And three things come to mind. The first is, this is a great opportunity. We engineers don't have to do all that much hard work. We no longer have to write UEM test benches. We don't have to prove assertions. We don't have to spend a lot of time reading specs. Computers can do that for us, and machines can do that for us, and specific algorithms can do that for us, and we can all go on holiday. Yes, it's a great opportunity. And then the more you think about this, the sooner you realize, hang on a minute, that means I'm not going to be needed anymore. So there's a potential threat here that we don't need engineers anymore, or we certainly won't need as many. And then there are those who think even worse. They might think that there's a bigger threat in artificial intelligence should it gain some notion of consciousness and be able to control human life. And you've seen the movies, you've seen the books, and so on. I'm certainly going to focus on the great opportunity that is presented to us through artificial intelligence and through machine learning in EDA tools. And so let me put a little bit of science now around machine learning. What is machine learning? It's a branch of artificial intelligence. And typically, this is the process by which systems can learn from data to recognize patterns. Okay, So we typically talk about a two-step machine learning process. We use what's called a deep neural network model, and we configure it to find patterns, as was described in the previous presentation. So we typically score each outcome and adjust these model parameters to improve the accuracy to recognize certain patterns, which can be values, they can be images, and so on. And this part is called training. And then essentially, we take out this feedback loop and we start to test the model with similar data sets to see whether it's accurate, and deploy and use the model on real data, expecting similar level of accuracy. And this is what we call inference. And there are many, many use cases where learning patterns from data can be useful. We're all familiar with image classification, face or person detection or recognition, object detection, speech recognition. We see this already today. And obviously there are use cases in EDA, and this touches EDA through its entire flow from design to verification. We may be able to use it, for example, to automate floor planning, so the engineers don't have to go and create the floor plan. You've probably seen stuff in the news that talked about success stories in this area. Again, I'm going to focus mainly on formal verification tools and functional verification when I'm talking about machine learning. So as I said, I'm going to touch on this from two angles. One is how you design machine learning accelerators and designs as a hardware implementation, and how EDA can help you verify them, and also how ML is used within EDA. And so to talk about the ML implementation as a piece of hardware, let me show you a typical example of a neural network. And you see this often. This is something that's fed a number of images of cats, and you want to basically train this and configure it to recognize the pet, which is the cat. And so at the heart of an ML neural network, you typically find a neuron. And this is simply derived from the human brain. And as you can see, when you design a chip that is ML able, you're going to need millions, hundreds of millions, if not billions, of instances of these. And this is typically a structure that receives a set of inputs. They're also referred to as activations, and using very, very simple mathematics. Although it's a lot of mathematics, there's millions of weights being multiplied and being added, and then compared to a given threshold. And then an activation function is calculated, and that leads us to making a decision. Is it basically a cat that we're seeing, or is it not a cat? So if it's a cat, yes, that's fine. If it's not, and this is what I refer to as the training process, we're going to compute an error and try and update these weights. And we go through this hundreds of thousands of times with the given application. Now, once the weights have been calculated and we gain a decent level of accuracy, we're ready to deploy it. So how do you design this stuff and make it hardware? Typically, these ML algorithms are written as C, C++, because they require a lot of floating point computations. And so there are several types of neural networks, recurrent neural networks, convolutional neural networks, or CNNs. So you'll hear these quite often. And typically they use 2D, 3D matrices as a calculation for their ML algorithms. And so to turn them into RTL, you're essentially going through a C++ or a SystemC model that uses a native floating point calculation, and you're trying to refine it to get to a bit accurate RTL. And typically this is something that goes through a high-level synthesis flow. But before you commit to high-level synthesis, you probably want to turn the floating point data types into a bit accurate data types. So that can be integers, or it can be a fixed point. And this is typically an iterative process that you go through to get to the right level of accuracy while maintaining correct results. And then you go into HLS, which generates a bit accurate RTA. So let me come back to this a little later to see how OneSpin can help with designing this bit accurate RTA. The other angle is how ML finds its applications in EDA. Again, I'm focusing on functional verification here. Some of the most common ones in simulation-based functional verification is stimulus and test generation. So the idea here is to help automate coverage closure by identifying coverage holes and tweaking the stimulus to hit that coverage hole without, us engineers involved in writing this, or at least suggesting what constraints or what assertions should be written or should be modified to decrease the time of verification cycle. And this is already deployed within EDA tools, and you can probably have access to it already today. As was presented in previously, so bug detection and localization, root cause analysis is another major application for machine learning in EDA. The idea is to automate the process of either tracing waveforms or predicting where bugs are going to occur, learning from a previous database of failures and their root cause, and so on. Now, from the OneSpin angle, in which we focus on formal verification, the two things that I've cherry-picked are automated solver strategy for theorem proving, because this is what happens inside the OneSpin formal tool. We're trying to find the right solver, the right approver for the right assertion. This goes beyond just prover orchestration, where you're taking turn from one algorithm to another. We're actually trying to predict from the type of design that you're reading the solver that's going to be successful first time. And you do that by automating the process of discovering the relationship between the logic that you're reading and the successful algorithm. Assertion generation is pretty much everywhere within the OneSpin platform. And essentially, instead of you and me, the engineer, writing the assertion to target a particular verification task, we let the tool learn the various data structures of the design and automatically generate those assertions. So with this in mind, please allow me to show you the OneSpin family of products and how ML is used either within the specific area of those products or can be used to verify your ML design. So OneSpin has a unified platform, essentially a single compiler that can read several languages, Verilog, System Verilog, VHDL, and SystemC, and a common debug platform, a linting platform. And based on this, a number of products are provided. So you've got DVClub, which is essentially the base product. You read the design in, and automatically you can generate structural analysis checks. You can generate activation checks to see whether the code executes, whether FSMs are reachable, and so on. You can check whether the design is going to be functionally correct, especially with regard to arithmetic operations and so on. All of this leads nicely into coverage through an app we call CCA, or coverage closure acceleration. Now, on top of this, we have built a number of automated apps. So the one that you're probably going to be most familiar with as a formal verification tool is obviously the property checker. Obviously, system Verilog assertions are supported, but we go beyond that, and there is also support for what's called operational assertions. I'm not going to spend a lot of time on this. It's a detailed topic, Briefly mentioning some of the other apps like XProp, fault injection automation, connectivity, control status registers, and the IP libraries, all are apps to help you automate the verification process using formal analysis. All this ties nicely within a methodology which once been referred to as the gap-free verification. Again, no time to go through this today. There are some advanced apps, and they do touch on ML design. So there's SystemC and C++ extensions, which we'll see is very much applicable to ML hardware design refinement. Connectivity XL is a different approach to checking chip connectivity by providing higher capacity. Floating point units is very much relevant to ML designs. As I said, many of the algorithms will use millions, if not billions, of add and multiply. So you need to make sure that these are functionally correct. And there is a RISC-V specific app for processor verification. The platform is also fine-tuned to target equivalence checking, both for ASIC applications as well as FPGA applications. And finally, there is a functional safety specific set of apps that target FMEDA, which help you generate all of the ISO 26262 metrics such as diagnostic coverage or fit rate. So which apps help you with ML design? So there's SystemC, C++ extension, the floating point unit extension, all help you with hardware design. As an assertion generation is one of the ML applications in EDA. These are used in control status register apps, the connectivity, the safety checks, and certainly the property checker uses ML algorithms to learn design structures and apply the right solver to the problem that is tasked to solve. So let me touch on those briefly. So if I elaborate on OneSpin for ML designs, as I said, SystemC is one of those apps. The solution essentially allows you to read your SystemC design. This could be at different levels of instructions. And using this, you can eliminate design bugs before committing your design to high-level synthesis. So you don't necessarily need stimulus, you don't necessarily need a test bench, and we can go and perform a set of automatic checks, checking things like design is initialized, we don't have any out of bounds, we don't have functions with no specific return values, data types aren't truncated, and so on. This allows you to optimize the design before committing to a high-level synthesis tool. The other thing that you can do is you need to go from floating point to a fixed point representation. And although SystemC gives you the data type to do that, it's very difficult to actually find the right bit width. You might have too many bits, that's a necessary complexity, too much silicon. Too few bits, and that would mean that you will have functional errors. And so the SystemC solutions within OneSpin will check for overflow automatically without the need for a test bench. And same thing with redundant bits. If there are any uppermost bits which are not required, it will highlight them. In addition to this, you can also leverage system variable assertions in SystemC designs. So you don't need necessarily to wait until you end up with Verilog or VHDL. You can apply this at SystemC stage and leverage it when you finished your high-level synthesis. Similarly, SystemC is not immune to X's, as it might suggest. It has the same issues as Verilog or VHDL. However, the SystemC language itself has no notion of undefined values or RTL semantics that generate X's. The OneSpin provides an extension that allows you to deploy X propagation for SystemC design. The other app that's useful for ML design is floating point unit. So this is a very, very specialist topic in its own right, and floating point computations are heavily used in AI applications. So if you're going to go into hardware, you need to make sure that this is functionally correct. The specs is horrendously complicated. There's many special cases, the normal, not a number, plus, minus, infinity, and so on. There is an app that allows you to formulate the correctness. So again, you don't need a reference model or a test bench or a test case, and it supports all operands, all rounding modes and exception flags. I invite you to go and look at this DVClub paper where a customer has used the app to verify their floating point unit. As you can see, it only requires minutes to find bags and minutes to get a full proof. Interestingly, it has support for the brain floats data type, which is used in machine learning, which was invented by Google Brain. Now, let me touch on machine learning within.
Thanks, Yassine. Unfortunately, we've run out of time at that point, sir. Thank you for your presentation.